Okay, this video is addressing this problem. The directions were to rewrite this expression right here without using summation notation. There's some basic summation theorems that are going to be used that are not posted here, and that's the theorems that allow us to get from here to here. The 24 over n to the 7th is really just a constant. Whatever number you pick for n, like if you pick the number 3 here, means that 3 to the 7th in the denominator, so I can pull 24 divided by 3 to the 7th power in front of the summation symbol because it's a constant. However, as k varies from 1 to n, we're going to be summing n terms of k times k minus 1, and the idea is, can we come up with a formula in terms of n instead of using summation notation? The thing I did here, k times the quantity k minus 1, and then I used another theorem about the sum of a difference can be broken apart into the difference of the sums. And I have separate terms in a red rectangle and a green rectangle, and I'm going to be using these two theorems about the sum from I equals 1 n or to n. You might want to try a couple of these. Let n equal 5 and add up 1, 2, 3, 4, and 5 and see if putting 5 in here gives you the same result. So that's what I've done below the black line. I have replaced the summation notation with its equivalent formula in terms of n. And similarly for the green rectangle, I've substituted, which is this one right here, for the sum from k equals 1 to n of k. Now it's just a matter of simplifying this as much as possible. I mean, this is a reasonable answer. I should have had one more. Oh no, I should have brackets here, because that 24 over n to the 7th is distributed times both terms in the parentheses. Okay, I would first notice that if I could get a common denominator, I might be able to write this as one fraction. So I'd multiply top and bottom of this second fraction by 3 to make this a 6 and this a 3. That gives me a common denominator. So in fact, I can now factor out that 6 and 4. But another thing that I notice is that each term on either side of this minus sign has a quantity n plus 1. So I'm going to factor out that n plus 1 and then see what's left inside the parentheses. I'll use another bracket here. If I factor out an n plus 1 from this, I'll then plus 1. I might as well distribute while I'm at it. I'll get 2n squared plus n minus, if I factor out this n plus 1, which I did, I'll get minus 3n. And while I'm at it, I'm going to 6, but I'm going to factor out the 6 and put it out here. And now I'm going to remove this guy, this formula, so that I have some room up on top. Let's get rid of this. And let's see what we can do. I'm going to first of all rewrite this first fraction as 4 over h to the 7th. Then in the parentheses, or in the brackets, I've still got this n plus 1. And this trinomial actually simplifies to 2n squared minus 2n. And I can see I can factor, oh, this is an n, not an h. I don't know why I wrote an h. Well, I can factor 2n from this binomial. So I have 4 over n to the 7th times n plus 1. And the 2n that I'm going to factor out here, I'm going to put out here. And left inside will be n minus 1. And now I'm starting to see that I can take this 2 times the 4 is 8. This n here will cancel out with one of the n's in the n to the 7th denominator and become n to the 6th. And n plus 1 times n minus 1 is n squared minus 1. So what we're suggesting is that 8 times the quantity n squared minus 1 over n to the 6th will give the same exact result as if you apply this formula right here by putting 1 in for k, 2 in for k, 3 in for k, and adding up the terms where this n, of course, is replaced by 3. So that is one way to write this expression, the original expression, without summation notation. Okay, I'm going to end the video, and I hope you understood that.